Hi everyone, welcome to this presentation entitled Parameter Estimation of Solar Photovoltaic Cell Models using a new hybrid metaheuristic algorithm named Nested Loops Harmony Search the Differential Evolution. My name is Belkacem Aoufi and I'm a PhD student at the University of Ouargla. This work is performed mutually with Dr. Osama Hashana, lecturer at the University of Ouargla, and Dr. Mohammed Amin Seed, lecturer at the University of Stif. As a summary in this presentation, firstly we are start by an introduction, which we are going to present the problematic and then the solution proposed to this problematic with some illustrations. Next, we are going to present the state of the art in this field of research. Then the proposed algorithm to solve this problem, and how does it work. Then we are going to present the results, which is the mean findings and the performance of the proposed method. And finally, we are conclude with conclusion and discussion with some perspective. So the problem is that we are going to find the model, the parameter of this, the photovoltaic model. Actually, the photovoltaic model can be represented with this equivalent electrical circuit, which is named the single diode model. The single diode model is could be represented by this mathematical equation. In this equation, we have five unknown parameters that they need identification. So how can we find these five unknown parameters from only one equation? The only given data is this IV nonlinear experimental curve. We can represent the photovoltaic model by two diode model as well, called double diode model. In this double diode model, we have 7 unknown parameters, which be represented mathematically with this equation. And for the second time, how can we find these 7 unknown parameters from only one equation? And the only thing that we have is the IV nonlinear experimental curve. So the solution, this problem, will be transformed into a numerical optimization problem by minimizing the difference between the measured data and the simulated one. As a fitness function or objective function, we are going to use the root mean square error. For the single diode model, the objective function is this equation, and for the double diode model, we have this equation. The block diagram of the proposed method could be represented a PV cell or PV module that we are going to measure the temperature and the voltage. We are going to measure the output current as well. The current, temperature and voltage will be used inside the algorithm to estimate the current. The current estimated will be then compared to the measured one, and then we are going to minimize this objective function. In this field of research, we noticed that a lot of metaheuristic techniques or algorithms have been developed to extract the PV model parameters, and it's still a challenge to estimate these parameters accurately. This field of research is very active and very attractive to research. We have proposed an algorithm called Nested Loops Harmony Search Differential Evolution algorithm, which is a hybrid method based on harmony search algorithm proposed by Guim and al. in 2001, and the famous differential evolution algorithm proposed by Storn and Price in 1997. Inner loop of DE is nested inside the outer loop of harmony search. Hybridization of two or more algorithms is widely used to estimate accurately the PV parameters. Hybridized techniques are often more performant. Usually they are more performant than the original ones. So we are going to introduce the differential evolution algorithm inside the harmony search algorithm. So how does this proposed algorithm works? First, we are going to start by the harmony search algorithm, which is a meta-heuristic algorithm inspired by the fundamental principles of the musical harmony improvisation process that is composed of the initialization of the memory of the harmonies. Then the step number 2 is the improvisation of new harmony, and then we are going to update the harmony memory. In differential evolution algorithm, we have 4 steps: initialization, mutation, crossover, and then selection. The differential evolution is characterized by the donor vector hi, which is produced by this equation, where bx, by, bz are 3 randomly chosen vectors from the current population vectors. This is the flow chart of the proposed algorithm. We have here the inner loop of DE and the outer loop of harmony search, and the algorithm is working as we can see. As a result, we found this parameter for the single diode model, and we can notice that the RMS is the best among these compared algorithm. For the double diode as well, we have the best RMSE and the corresponding 7 parameter. The performance of the proposed algorithm is evaluated and validated using a real measurement of the IV characteristics RTC France silicon PV cell under an irradiation of 1000 watt per square meter and a temperature of 33 degree. That are the best for both single diode and double diode model. The reliability or the stability of the algorithm is measured by the standard deviation, which is very small value for each and small single diode and double diode model, and the conversion speed is about 1 second for single diode model and 3 seconds for the double diode model. As we can see, this represents the measured and estimated values for both single diode and double diode model. As a conclusion, we can say that to identify the unknown parameters of single diode and double diode model of the photovoltaic system, a hybrid optimization technique is proposed. It is based on combination between harmony search and the mutation and the selection operators of differential evolution with nested loops. Depending on the results obtained, the proposed algorithm shows the best performance in terms of accuracy, reliability, and conversion speed. The nested loop harmony search differential evolution is promising candidate approach for solar PV model parameter extraction. As a perspective, we are going to use this proposed algorithm to estimate or to extract the parameters of photovoltaic commercial modules. This is a list of references that we have used, and finally, thank you for your attention.